Alright, everybody, we're going to go ahead and get started. Hi, welcome to day 2 of ShellCon. Thank you so much for shaking off the hangover and coming out a little bit earlier. So, I'm super excited for this morning's keynote. So, several months ago when we were first doing our CFP, Sammy had sent in his proposal, and we need to work on your titles a little bit because it like, I was like, okay, that just sounds like a regular technical talk. And we read the description, and we were like, oh, that's awesome! That was actually the noises that I made. So, the idea then was that, hey, this is super cool. We really like Sammy. He's been a friend of the con for a long time, so let's have him keynote. Without further ado, Sammy Kamkar, everyone.
Thanks, everyone. Yeah, friend of many people here. First time at the con, so I'm really excited. And yeah, I want to share a project I've been working on. So this is the first time I'll be talking about it, demonstrating it, etc. So this should be fun. So this is called NAT Pinning, and it's a update from an earlier version from 2010 that I did. It's a super simple proof of concept, but first let's just talk about NAT in general. NAT is network address translation. So most of us are going to be familiar with NATs. We typically have a router at home that is on our network connecting to multiple devices. Some of your routers, some of your networks will look more like this. Now, what is a NAT? So a NAT is a device. That's so funny. So a NAT is basically a device that allows to have multiple devices on a network use a single public IP address. So you may have heard that we're running out of IPv4 space, and that IPv6 is totally coming. It's soon to be here in the next 10, 20, 30 years. We'll all have it. But until then, we used to have all of our devices on public IP address space. So when you would connect your DSL or a cable modem, really that's just a public IP address that is accessible from anything else across the internet. Then router manufacturers, basically routers came out and they had network address translation, and firewalls have this as well, where they will have internal subnet. So you have devices on top, and those will have internal IPs like 10.0.0. whatever, or 192.168.0. whatever. And those are only accessible within your network. And then they'll hit your router, and your router will then translate that to the public IP and reach whatever you're trying to, that's your router. And in many cases, a router will also be a firewall. So in reality, the router will actually protect you from ingress. So if someone is trying to connect to a device on your machine, they won't be able to because the router will block it, unless you explicitly set up port forwarding, DMZ, etc. And now one thing to, what NAT pinning is, the goal of NAT pinning is to bypass your NAT. So as an attacker, I'm an attacker, I think. It's a lot of fun to attack things. And I want to bypass someone else's NAT. So you have a NAT at home and you have some devices on your network. I want to be able to access your devices as if they weren't behind a NAT or behind a firewall. And why is this interesting? Well, this is an LSOF output of my computer. I have something like 20 or 30 services that are just listening. And most of these are actually on public space. So that means if you're on the same network as me, you can talk to all of these devices, all of these applications. So Sonos, I don't even use Sonos. I don't even have Sonos, but I have a Sonos application that's running on my computer 24/7. I didn't even know that until I did this, until I recorded this LSOF output. I have like a bunch of random Node clients, and these aren't Node.js things I'm running. Parallels is just listening for whatever. Who knows? Spotify. So I use Spotify, but that means it's listening publicly. So anyone can connect to Spotify on 2 different ports it's listening. So who knows what those are, right? There are going to be so many vulnerabilities. There are actually a ton of remote execution stuff that came out just this year. Now, normally, you are protected, at least from the public, by your NAT. But we want to attack. So the way NAT pinning works is, the ultimate goal is we want the victim, let's say a victim machine, to visit a website. Because that's pretty easy. Pretty easy to get someone to visit a website and that may be a malicious website, or that may be a non-malicious website, where we have malicious advertisements, right? If you just pay Facebook and get some JavaScript running, then that is just as good as getting them to hit a malicious website. So let's see how we can do that. But let's learn a little bit more about NAT and how it actually tracks connections. So NAT itself will look at, this is an IP header and the TCP header of a TCP packet. Let's say you're connecting to a web server on port 443 or 80. You're going to send these IP packets out, and you're going to have a source address, which will be your internal IP address, like 10.0.0.2, and a destination, which is whatever, Proto.com, or the IP address matching to that. You'll have a source and destination for it. And those will be tracked by the NAT. Let's see, I have a video here. It might be difficult to see some of these IPs. But essentially, on the top, I'm sniffing from my local machine, and from the bottom, I'm sniffing from the remote machine. And here, basically, we can see that my internal IP 10.5.1.198 is connecting out to a 104 public IP. But on the bottom machine, it doesn't see the 10 dot, it sees a 207 dot, which is the public IP. So that's the conversion that's occurring. Now, there's something in NAT that we see that's pretty interesting. As routers came out, we started to do things like, we tried to use things like FTP. And FTP stopped working as soon as people installed NAT. And the reason is, FTP uses multiple ports. So when you're FTPing somewhere, you connect to port 21. Hopefully you're not FTPing anywhere. But if you were, you'd connect it to port 21 on some machine, and you would say, this is a real example, well, maybe not FTP, but something like that. And you would say, you'd send a port command, and the port command says, hey, connect back to me on this IP and port. And when your FTP client opens a second port, and it's now waiting for a connection to come back. So when you say list, I want to list all the files, that's not happening over that FTP session. That's over a second connection. And what's really cool is that this is an inbound connection, not an outbound connection. So your computer, your machine, is now opening up this port 123, and it says, hey, FTP server, just connect back to 123. Now, as soon as you're behind NAT, that breaks, it just stops working. So what did NAT vendors do and router vendors do is they implemented something called application level gateways, or ALGs. And what these do is they inspect traffic, right? It's basically deep packet inspection. So they are actually now looking and they say, oh, you know what? I know port 21 TCP is actually typically used for FTP. So I'm now going to watch the commands. And if I see a port command get sent out, and it says, hey, connect back to me on port 123, I'm then going to port forward 123 back to this person when I see that server connect. So maybe we can use this to actually connect through someone's LAN, even if they're not maybe doing an FTP. Now, what I'm trying to learn, I mean, a lot of this stuff may be basic to some people, but I'm just going to go over some of the things that I used to learn. So I'm always reading RFCs. If I want to know how something works, if it's a protocol, well-defined protocol, then there will be an RFC on it. So you can always check those out. And you can see how the port command and other things can work for FTP, for example. Now, in 2010, when I started playing with this idea, I found that they started restricting ports. I basically had a prototype working, and then there was an update to, I think it was Firefox or Chrome, where they added a port restriction list. Because I was thinking, okay, maybe I can use the web browser to do an HTTP post and send FTP commands on port 21 and control those commands in the post data. The problem was the browsers then started blocking ports. So here's actually source code from Chrome where you can see they're blocking port 21. Around that time, I was playing around and was thinking, okay, well, TCP ports are 16 bits, so there's 65,536 possibilities. What if you give a port that is larger than 16 bits? What'll happen? And essentially, what'll happen is, in many cases, it will overflow, and you'll be only be left with 16 bits. So what if you create a form, an HTTP form, and you send it to not a 16-bit address, but a 17-bit address? And that 17 bits is the port you want, in this example, 6667, which is IRC, plus 65,536, which is just a 1 bit in the 17. Well, what happens is, and here's a C example, like if we take port and we set to 65536 plus 1337, and then we print it, we get 1337, assuming we only have 16 bits of space. So that extra bit of data gets dropped. So what if your browser is looking at the string in your form and says, oh, this huge number, larger than 16 bits, isn't in my restricted port list. and then it sends it along to the TCP stack, which is in libc, and that only has 16 bits of space. It now drops that extra bit, and you just bypass the restriction within the browser. So now you can connect to any port you want. So that's pretty cool. So here's an example. Here's an example of IRC. IRC is actually what I ended up using just because I really like IRC. So here is, I've just selected in green what I would send to an IRC server router connecting. You have your username, you have your nickname, I set my nickname, and then I send a private message. Not a big deal. Now, what's interesting about IRC and why I selected IRC as an example is because it's very similar to HTTP in the fact that it's new line terminated, right? Many protocols are binary, but HTTP is in port 80, not TLS. And IRC are both new line-based, text-based protocols. So when you're connecting to an HTTP server on port 80 and you say get/HTTP 1.0 host whatever, that's all, every command is on the new line. And what's cool about that is if you do a post, you say post and then some headers, and then you control the content of that data. So if your application level gateway is now looking at this and says, oh, I'm looking at FTP, or maybe I'm looking at IRC, and I see, okay, I can create a form. No, do that here. We can create a form in JavaScript, generated, added to a page. We'll then connect to our port 72203, which again gets overflowed by our IP stack and turns into 6667. This form now connects to 6667. Your ALG on your router sees an IRC connection, even though your browser is talking HTTP. So now you've confused the router, but it doesn't know that. It has no idea that your browser is communicating on 6667. It assumes it's IRC. And you now control this post data within the content of the track, which is really cool. You can put whatever you want. And it is looking line by line. And your router's like, okay, post/, I don't know what that means. I don't know that IRC command. I'm going to ignore it. Post, colon, whatever. I don't know that line. I'm going to ignore it. And then it gets to the content. And it's like, okay, I have this data that looks like IRC traffic. Well, the cool thing about IRC is you can send a DCC chat or a DCC file. And DCC works just like FTP, where you're opening a port on your computer, and your really great router is very beneficial and very helpful here. It says, oh, they're trying to open port 22. I better forward that back to the user. Now, I was trying to do this. The only thing is, in the very first line, you'll see that the way that DCC works is you say private message, username, DCC chat, my name, IP address, and a port. Now, what's cool is we define the port, which means we can select any port we want to port forward, but we have to know the IP. Now, when I was trying this, I was just using the user's public IP address because I can get that from the web server. But that wasn't working. And I realized because the router is specifically looking for the internal IP. So how do we get the internal IP address from a browser? In 2010, there was something called Live Connect. Has anyone heard of Live Connect? Good. Yeah, that's good. It's Java in JavaScript. It was in Firefox for like 2 months before they realized this wasn't a good idea. But during that time, I got to use it, and that was really nice. So here's Live Connect code. So essentially, you're able to actually use Java classes, factories, whatever they are, and then to get local IPs. That's why. Because then you can actually get a local address. You can find the socket and then ask this Java factory, hey, give me my local IP address. You now have the internal IP address of the user, right? Browsers normally don't reveal that information. Now you can take that and update the private message DCC chat, and now the router's like, oh, this is a totally legitimate DCC chat. I better port forward port 22 or whatever other port. And in your post data, you don't need to do one port. You can send multiple DCC chats. You can send 65,000 DCC chats if you want, and open every single port back to the victim, just by them visiting a website. Now, unfortunately, that was 2010. So Live Connection no longer exists. It was there and gone. And they fixed the overflow, TCP/IP overflow thing. So I was kind of playing with this recently, and I thought, all right, are there other mechanisms that we could use? So I went through Linux NetFilter. NetFilter is Linux's IP stack, and it's very convenient because it's open source, so you can see how it behaves. And the first thing I did was I made this spreadsheet. And this spreadsheet is all the application level gateways that Linux supports. So it has SIP, FTP, IRC, some stuff I never heard of, like Sane, I think is a backup service. Amanda, I don't know what that is. And some other VoIP stuff like H323. And then I went into Chrome's source code, and I saw, okay, what are the ports that are restricted? Because we can't do that port evasion technique anymore. That doesn't work. And the ones that aren't blocked were Sane, again, never really heard of that. SIP, which is 360, and PPTV. Oh, and one of the H323 protocols, which is the voice over IP. So we're looking at what Chrome doesn't block. So I thought SIP was pretty good because SIP is pretty common. That's a voice over IP protocol. Virtually every IP phone speaks SIP. And SIP is basically like FTP, but for sound. So with SIP, the nice thing about SIP, and the reason I didn't choose Sane, is because SIP is also a new line-based protocol. And the benefit here is that the router can ignore the lines that we don't know, and will look at the lines that it doesn't, for example, in the middle of your host. So I attempted to do the same thing, but I ran into this issue. And SIP also needs the IP address. You need to include your IP address. So this wasn't working. So I was like, okay, maybe we can use some like an IP discovery some other way. I started looking at what are all the features in the browser. We'll go over some of that in a bit. But basically, I'm going in Chrome. I go to like Chrome://flags, and I see what are all the experimental features. I'll go to W3's website and look at some new standards that are coming out, try to understand what are the new things that are available. And I found it's called web+RTC. And web+RTC is pretty cool. It's for peer-to-peer audio and video. And in order to do peer-to-peer audio and video, it's pretty easy if it's over the internet because you're just hitting some public IP. But if you're doing it internally on LAN, you need to know the IP address, the internal IP address. So for that mechanism, they've introduced ICE, and ICE supports stun and turn, and technically it supports some other stuff, but stun and turn essentially determine what type of NAT you're behind. So your browser has this ability with web+RTC to connect to a stun or turn server, and it says, hey, you're on this type of NAT. And also, here's your public IP address. To make web+RTC work internally on a network, you will actually connect directly to the local IP address. So the browser now gives you the local IP address. So this is pretty exciting and basically makes this attack work all over again. This was super exciting until I was making the presentation last night, and it wasn't working. So I refreshed, and I took a screenshot, and apparently they just fixed this. So now the browsers don't give you an internal IP address. Instead, they use Bonjour or MDNS, and they generate a .local address, which only works on your network. So I actually don't know the local IP address anymore. Instead, you get this like weird hexadecimal, UUID looking thing, .local, and that is only accessible within your network. This sucks. Anyway, thank you, everyone. So that didn't work, and that was troublesome. So I started playing around, and I don't even know what the video is. So we're doing a TCP dump here. Oh, okay, so this is cool. So we're doing a TCP dump here. So here, I'm doing something. On the top, I'm just doing a TCP dump of two different IPs on my network. One is 192.168.0.2, and the other is .123. .2 exists. .123 does not exist. And on the bottom, I do a netcat. So I do a netcat on .2 to a port that isn't open, and that's 79. And immediately it says connection refused. And the way we know the connection is refused is that TCP sends you a packet called RST, or reset. And that's how you connect somewhere, and it says immediately, no, there's nothing open on this. However, what that means is there was a host there. Now, if the port is open, like on port 80, which I also did, then you don't get an RST, you get a SYNCAT. And that is to start essentially a three-way handshake. What is interesting about those two is that they return immediately. But when you hit a .123, what was happening is you send a bunch of ARP requests for a host, and nothing gets responded. So it basically times out after whatever your local timeout is. So what if we could abuse that from the browser? What if we create an image? And we send an image to just a random IP address for now. If that IP address exists, and let's say it's on your network, it will return. Essentially, and you add event handlers on error and on success. It will either error because the port's not open, but the machine is up, or it will succeed because the port is open and the machine is up, or it won't error until 10 seconds later. But if it errors immediately, that means it exists. So what if we just take the top most common gateway IP addresses, like 10.0.0.1, 192.168.0.1, and then do that for there are basically 256 of these that are quite common, and we do that for every one. And we say in this code right here, we generate an image in JavaScript. It's just pointing to HTTP:// in this case 192.168.0.1. And then we send it to a hidden, so you don't see this image. It's not a real image. And we have two event handlers, on error and on load. And all those do is they time. And they say how long did it take to either succeed or error. And if it's less than 1 second, we know this host exists. So it runs for 250, 300 hosts. And in 1 second, you now know, oh, this gateway exists. 192.168.0.1. 10.0.0.1 does not exist. So now I know what the gateway is. So then you repeat this for all 256 or 255 IPs on that subnet. And you're going to get a bunch of hosts. But what's really nice is you have microsecond precision in JavaScript on your browser, and you just see what responds immediately. That's going to be your computer. So your computer is really fast at talking to itself. It's like way faster than talking to anything else in the network, because it only has to go to loop, which is super convenient. So here's an example where it was trying to create web+RTC, which totally failed. And then I have this local subnet code. And basically, it sees .107 has responded the fastest. And then I'll pull up terminal, run IP, and we'll see .107 is my IP address. So we now have modern. So here's the actual SID packet updated, right? So now you go through that, you determine the local IP address, and now you get to the correct IP address, the local IP, into the SID packet, and let the router ALG do all the rest. Except it's not working. And I'm like, okay, don't know why. So next was to figure out, well, why is it failing? I would switch back to IRC, which succeeded for me 10 years ago. The problem is IRC is blocked, right? We need to find something that Chrome and Firefox and Safari and IE and Edge don't block. And 5060 was basically the only one that looked promising. So how do we understand how a router works? Well, I mean, let's look at the firmware. Or I mean, let's open it up. Really, if you want to understand how something works, you open it up. So we'll go quickly. I'm just going to go through some of those tools that I like to use. There's lots of other talks, and we only have so much time. So one thing I use a lot is actually my phone. And the nice thing about the phone is, it allows you to see things really well because you can zoom, right? You can magnify, and that's super useful, especially when you're trying to look at circuits. Another thing that's super useful about your phone is that it has a light. So if you enable your flashlight and put it under a circuit board, you can then see traces. It's very useful for seeing where traces go and looking through multi-layer boards. When you're looking at a PCB, if you know nothing, I knew nothing about circuits or electronics a couple years ago, so it's just by like opening things up and starting to look at them did I learn more and more, because I just wanted to understand how can I exploit this in interesting ways. And when you start looking at chips, then you look at the names, and you can Google those names, and often you'll find public data sheets. So you can download public data sheets to see how that chip works. Micro probes, these are super useful. So these are little tiny probes that can grab onto really tiny pitch pins on chips. This is useful for if you're trying to dump firmware and you want to grab onto a couple of pins on some chips. This is an example of SPI chip. So this is actually a SPI flash chip, excuse me. So this will actually contain the firmware for a router, for example. Logic analyzer, I like to use Salient logic analyzer. I just want to give you guys the basic tools that I use that will quickly allow you to extract firmware from devices like routers. And for glitching, I will be doing a talk in, I don't know, a month or two on glitching using really low-cost FPGA. So that's pretty cool, but there is another tool called the Chip Whisperer, which is an amazing device and project. It's an open source open hardware device for glitching attacks. You can do all sorts of things like extract ADSPs from devices by doing power analysis. You can enable bootloader protection. So there's really cool stuff. When you have say a microcontroller and it's booting up, often vendors will enable bootloader protection or debug protection. That prevents some people like us from going in and saying, hey, I want to enable debugger and access the flash, access the memory so I can reverse engineer it. So when in development, they don't have that enabled. But when they go to production, they enable it. Well, the way that works is when the chip is booting up, the bootloader runs and says, okay, I'm going to execute this instruction and check the value of this fuse. Is this fuse set that says don't allow debugger? Now the thing is, all these instructions that are running on the CPU or microcontroller, they take time, right? It takes time to do that. And time is controlled by a clock. So if you can take something like a clock and you can glitch it, you can say, okay, it takes 10 nanoseconds to run this command. So normally the clock is square wave. And you say, you know what, normally it takes 10 nanoseconds. But for this one cycle, we're going to make that 1 nanosecond. So the transistors don't even have enough time to check. And it just skips the next cycle. You just skip that check for that. Now you have to automate these because you're not gonna know which clock cycle it is. But you just automate it. So you say, okay, first wait 1 clock cycle in glitch. And then if that doesn't bypass the debugger protection, wait 2 clock cycles. You automate it and you sit there and half an hour later, you get full access to that chip, that memory, and then you can dump the flash. And now you have binary. Another way to get binaries, depending on the type of router, look online, right? In many cases, binaries are and firmware is available online, many times unencrypted. The correct thing for them to do is actually encrypt it, but many cases they don't. Here's an example I found. I found a zip file online, I downloaded it, I unzipped it, I used binwalk, which wasn't able to work for me on Mac OS, so I ported this. I ported some stuff to make binwalk extract this type of file. This was a squash FS file. And then I used unsquash FS, which also didn't work on Mac. So I had a GitHub. And I put links in all of this, so I'll make these slides available. So I made a fork of the squash FS tool so you can run on Mac. It runs fine on Linux. And this will unpack the firmware for this router. Once we start going, these files don't look that interesting, so we'll just keep looking now for FTP. And I find some binaries here, so some of these might be interesting. And KO is a kernel object. So I'm like, okay, there's probably some cool stuff there. So it's a 32-bit ELF here. We could run strings on it, look at some of the words in here, FTP code. That sounds pretty reasonable. So let's reverse engineer that. I thought it'd be good to learn this Ghidra. All right, Jahidra. So this Jahidra is a tool from NSA, which is pretty cool. Around the same time, I think Microsoft got jealous. They saw that NSA released this awesome reverse engineering tool, so they open sourced a calculator. And it's literally an awesome reverse engineering. I typically use IDA, but I'm also a fan of low cost and open source tools, so I try to use those when available. So we'll just take a quick look. We won't dig in too deep here, but we see FTP decode, which is a function here. And that gives us a reasonable inclination that maybe there are other decode functions, right? Because we really want to understand why isn't the SIP packet working? And we look some further and we see here, there's a SIP decode function. All right, cool. So if we look further in SIP decode and we look in graph view, there's something interesting here. It's loading this string called invite. And invite is a SIP command. So register is another SIP command. These are just SIP commands that are at the beginning of a SIP packet. And we're doing a string case compare. And we're jumping to somewhere if it's 0 and not, and otherwise we're failing if not. Essentially what it's saying is the beginning of this packet start with register or invite? And if it doesn't, I'm ignoring it. So the entire packet, which normally in our HTTP example is HTTP is post, right? When you send an HTTP post, the first word in the data portion of your packet is the post. And unfortunately, we don't control that, right? We control post. We can make it a get. We might be able to trigger a head or options. But we can't just arbitrarily control the data inside the packet. We can only arbitrarily control the middle portion in the post content. So the problem is modern routers look at the SIP command. They don't just ignore it line by line like they used to 10 years ago. They're actually looking at the very beginning of the packet. So this is kind of a problem because I don't control that portion. So as I was saying, like maybe there's some other techniques that we can use. Maybe there's some other protocols I can use other than HTTP to try to bypass this. So I started looking through Chrome //flags, looking for experimental features. You can go to the Chrome source and start looking for sockets there. I started going to w3.org and looking through their standards. And in this protocol, I clicked protocol, and everything is just like, what is topic? Explanation is what it says. And it's like, what is topic used for? Explanation. That's literally what it says on the website. But there's actual standards for actual Things are actually well documented. So I started going through things, and there's HTTP, HTTPS, FTP, WebSocket, DNS. These are some of the things that modern browsers support. And I was looking at stun. Now, stun is something we saw with WebRTC earlier. And stun is pretty cool because it is, I started playing around with it, seeing what we could do. And stun is over UDP. And as I was playing with some of the values, you can play with the username. And the username is in plain text. So stun itself is not encrypted. There is turn and there's encrypted turn. There actually is encrypted stun, but it's not implemented in the browser that I can find. So stun itself is unencrypted, and you can set a username. And that username, I just like playing around, and I set the username to hello, is it me you're looking for? I can see it in your eyes, I can see it in your smile, with new lines, and it just included everything. So there's actually no character limit to the username in stun in browsers today. So I was wondering, what if I send a lot more data? Like a lot more. At some point, something's gonna break or overflow or something. Unfortunately, I didn't have any buffer overflows, but the packets didn't have to break up at some point because your Ethernet controller, your Wi-Fi can only have a maximum transmission unit. It's IP, so IP at some point will fragment. You will get IP fragmentation. And I was thinking, well, is there a way that you can maybe calculate that and then figure out where does it, when it fragments? If I'm sending this really long username, right? We have this stun packet, it's all the stun UDP stuff, and then the username, and then it overflows. Well, if it overflows, it will then send another packet. And this is the beginning of a packet that I potentially have arbitrary control of. So if I can measure where it's going to fragment, then can't I just intentionally insert something that is now the beginning of a secondary packet? And I now have arbitrary UDP control. So the answer is yes. You can do that. So basically, what I've done is I generate a stun via JavaScript, a stun request with a really long user. And then I have a stun server that's listening on my server, and it says, okay, at what point does this fragment? And at that point, I then send back to the user. Basically, the client has a WebSocket open to me as well, secondarily. And through that WebSocket, we send back, hey, this is the size of your IP packet. This is the size of your IP options. This is the size of your UDP packet. This is the total size of that packet before it overflowed. And so now what you want to do is you want to send a single arbitrary packet with the username long enough that it gets exactly to the single byte that then overflows, and then you send your SIP packet. Now that is pretty cool. And what that allows you to do is open any UDP port up, all UDP ports, and then port forward them with the victim doing nothing but visiting the website. Now this was pretty cool, except that it's UDP, and UDP is pretty boring. We want TCP because all the cool services are TCP, right? Except maybe DNS. So TCP, can we do the same thing? What if we send a post, and we just send in that post data just a ton of stuff? There's some dead pixels on my screen. I don't know what that random circle is. So if we send a bunch of TCP post data, right, we only control that bottom portion. And I just send arrays and underscores. And then we send our SIP packet. Can we do this again? We can then have a TCP server listening on TCP 5060, and that's the nice thing about SIP is that it works for both TCP and UDP. So you send an HTTP post, which is massively large. You can also get a little bit of control by massaging the TCP message size. I forget what they call it, TCP-MS or something. But essentially, when you connect to something, the server can say, hey, I only accept packets this size. So that makes it even easier. So you can have the connection connect to you. You then respond, hey, I only accept packets of this size, and then you already know where it's going to work. At that point, you get these perfect precision control on the second packet. The second packet is the beginning of the post, but it's on the third packet where it's hard to see, but you have a SIP command, and then there's our original SIP command with our internal IP address, including the port number that you want to open. And you can perform this in a loop and do this for 65,000 ports. And you literally just enable DMZ on someone's router just by them visiting the website. This is essentially what happens, right? The victim visits a website through the internet, through their router, through the internet, hits the website. The website could just load your JavaScript, your evil JavaScript. So it could be a normal site, and you can be a malicious advertiser. Then it sends this data back, and your browser does all this automatically. It doesn't request anything from you. And you get arbitrary packet injection through their ALG, which is pretty cool. This is a simple example. It's going to be hard to see any of this stuff, but essentially, it begins running. First, it determines what is the subnet, and then on that subnet, it determines what are the ports. I don't know this again. Is it replaying? It sends a bunch of large packets. It measures the size of the packet. It returns what those sizes are. Then it generates a post on the background, and it generates the SIP packet. It sends the SIP packet, and we even validate on the server side that the SIP packet was received properly, because what happens is the router will change the internal IP address to the public IP address, so you can validate that it was succeeded properly. And the SIP server that's running responds in both HTTP and SIP back to the client, so the browser actually closes the connection properly, and the SIP and the router thinks it's totally legit. And fortunately that works. And that is NAT Pinning. So thank you so much for listening. I'd be happy to answer any questions.
Please, let my computer ask questions.
Yeah.
Awesome talk. Thanks. Who's your preferred smart format here?
Well, I'm not going to say anything, but my company might be working on. I don't think I have a preferred vendor. Just whatever's on Amazon.
At the beginning you mentioned IPv6, which most devices supported prefer IPv6 when it's happened.
Well, I only mentioned IPv4, so I was insinuating IPv5. But we can jump to 6.
Right. So with IPv6, there is no real matching because there's no need for it.
Okay.
Is there any way to transition once you get an entry with the IPv4 to retrieving the IPv6 address?
Good question. I'll talk to these guys. I think these guys have done some know a lot more than me about that. So I don't know the answer to that question. Do you want to answer?
No.
What is the actual difference that you usually see between when you pick your own IP versus an adjacent IP? So when you're doing like the internet speed, and then also I saw on one of your last slides that 255 responded even faster than your local.
Let's see here. They're pretty close. So 12 milliseconds is 107, and then 16 is 108. You're right. 205 is broadcast, so that is also myself.
Yeah.
So we're talking milliseconds.
Yeah.
But you get microseconds, it's just show milliseconds.
Yeah.
So it's quite reliable. I will mention that, I probably just need to make that a separate project because it's a useful JavaScript library. I don't hit everything simultaneously, so I do it in bursts. So I hit 5 IPs at a time. You don't want to make your browser do too much because they might actually lose it. I found that when I tried to hold them, like 100 IPs at once, that didn't work. But this is reliable.
So, real question. Just curious, if the WebRTC change was a specific browser update.
It was definitely a browser update. I am running beta on, I run beta Chrome, so I don't know if, and Safari doesn't do it at all, so it doesn't return anything. Yeah, so they just started removing this. I've been sitting on this for a while, and I just went back to do the presentation. I was like, oh no.
Again, nice work.
Thanks. Yeah, so at some point they did that, and it's actually a really good idea how they implemented that mechanism, because the .local is accessible over the network, and it's meetings outside of the network. I would be curious, what is their seed? How are they ranking their IDs? Where does randomness come from in the browser? What is the seed? So I'd be curious what that is.
Hi, I came a little late, but I noticed a lot of
I can start again.
Perfect. So a lot of the exploits regarding SIP and so forth. So if you're on the other side of the fence there and you're trying to make SIP defensible in a company or whatever.
Yeah, that's a good question. So you're not necessarily exploiting SIP, you're really exploiting the router potentially, and maybe the browser. Oh, I mean, I'll add some other things, but what I would suggest in this scenario is disable SIP ALG. So if your router allows you to do that, definitely commercial stuff will do that. Not all the consumer stuff allows you to do that. However, that means SIP will stop working. So it also means you can't use voice over IP, unless you then intentionally port forward, but then you can only have like a single voice over IP. So it messes things, it makes things messy on like a real network. You could make the NAT smarter, and you could say, oh, you know what? Let me validate whether this was like a TCP segment. But that's not guaranteed because you can, like, it's easy with IP fragmentation to determine this is a fragmented IP because you can see that in the header. I don't think you necessarily see the TCP. But there's some other cool stuff. So for example, I forgot to mention that in the churn stuff I was doing, when I was starting to look at these other sockets, these other mechanisms to produce sockets in the browser, all those restricted ports, those only apply to HTTP, HTTPS, basically URIs, right? So if you're trying to do an image source or a form or something, as soon as you go to churn or stun, you now have access to all those restricted ports because they're only doing that check in that one location. So you can actually bypass restricted ports in many ways, I'm sure. So you might be able to do some cool stuff with that. Also know that Firefox actually made this a little bit more challenging because Firefox, when you have your HTTP post, there's this WebKit content line that is essentially the delimiter for your post. I probably have a post. But basically, the problem is that string would change lengths. So even though I knew the length for the first post, as soon as I determined what the length was, it would then change. Fortunately, it was only within a few bytes. So if it detects Firefox and it sees that length changes, it just sends it a couple more times. And after about 4 requests, it will hit successfully.
When you're digging around in the firmware for a router, obviously that's for one specific router. Do you find that what you found there is pretty broadly applicable to consumer routers?
So I was specifically looking at multiple routers. So I was dumping flash from some routers, I was extracting binaries from other routers, or downloading binaries from other routers. Yeah. So that was the nice thing about SIP is that it's pretty ubiquitous.
Did you look into trying to figure out the net mask of the network in order to maybe reduce the number of IPs to try to find and discover?
I didn't. That's the idea. You could probably just hit the 255, and then if it doesn't respond, then you know you're not on /24, right? And then you get to the next 255, and technically you get a net mask that's not just +Cs. But I suppose what you could do is actually you could just keep doing this until you hit something that is similar. As Chris noticed, the gateway, broadcast was similar, if not faster, than your own IP address. So you just look at it maybe faster. That's how. And then after that, if you get no responses, then you know that that's your broadcast, and then you know your net mask. But I never played with that. That would be cool. I think we should definitely iterate on this local IP discovery stuff. That'd be cool.
How long does the port forwarding stay open for?
That's a good question. I don't know. I don't think it's a long time though. I was thinking I don't think it's a long time, but you know it's happening because they hit your server, right? They basically hit your server, and then you send something and said, "Hey, open up this port," so you know exactly when it's happening.
Are WebSockets a binary protocol? And if you control, are they plain text and would that be a better candidate for raw packets and packet side of things? If they have the port restrictions.
You could probably do it over WebSockets, but technically WebSockets is a feature on top of HTTP. So you end up having an HTTP socket that you generate, and then you send, I think it's an upgrade request, and the upgrade request that says, hey, I want to upgrade to WebSockets. And then within your WebSocket, you could probably do the same. I don't know if there's any advantages or disadvantages. What's that?
Does it continue to put the imply at the port restriction?
It probably has the port restriction, but you know, let's get it. Super testing. What is common?
Explanation.
All right, thank you so
All
much.
right, awesome. Thank you.